Okay, next we have the corresponding theorem, Lemma 275 in this book. So in this lemma we are given two groups G and G bar, and there is a homomorphism phi from G onto G bar, and the kernel of this homomorphism is K. Now this thing is given under these conditions. We have chosen a subgroup, any subgroup H bar of G bar from the second group. Then we have to prove that the subset H of G defined like this is a subgroup of G. H by definition is the set of those elements in G which are mapped by the mapping phi onto elements which are in that subgroup H bar of G bar. We have to prove that this H is a subgroup of G, and also it contains the kernel of phi. Furthermore, if our original subgroup H bar of G bar was chosen so that it's normal in G bar, then this subgroup H will also be normal in G. Moreover, this association, that is, you have chosen a subgroup of G bar, for that you have got a subgroup of G that contains K. This sets up a one-to-one correspondence between subgroups of G bar and subgroups of G containing K. So the author says, moreover, this association sets up a one-to-one mapping from the set of all subgroups of G bar onto the set of all subgroups of G which contain K. So this is the correspondence between subgroups of the second group and subgroups of the first group containing K. So let us see how one can prove this. The proof is quite straightforward. I mean, you just have to go through all the things, verify each one of them one after another, and the proof will be over. Okay, so in this proof, our first job is to show that this set H is a subgroup of G. Clearly, from the definition of H, we see that H is a subset of G. That's the first thing. Since phi of E is equal to E bar, this belongs to H bar, where E bar is the identity element of G bar. We already know that the identity element of G is mapped onto the identity element of G bar by any homomorphism. So that's why phi of E is equal to E bar, and since H bar is a subgroup of G bar, E bar will be in H bar. We have E belonging to H, but then by the definition of H, E will be in H, and as such H is a non-empty subset of G. Now let G1 and G2 excuse me, be two elements in H. Then by definition their phi images will be elements in H bar, since H bar is a subgroup of G bar, we have phi of G1, G2 since phi is a homomorphism, phi of g1 g2 will be phi g1 phi g2. This belongs to H, and phi of g1 inverse this also belongs to belongs to H bar. Okay, because these are elements in H bar and H bar is a subgroup of G bar, so the product of them and the inverse of one of them will belong to H bar again. But then we have, but then by the definition of H, G1 G2 will belong to H, and so will G1 inverse. Thus, H is a subgroup of G. Next, we have to show that H contains K. H contains the kernel of phi. These bugs are creating a hell lot of problem. Let K be any element in K. Then, since K belongs to the kernel of the homomorphism phi, so phi will map K onto the identity element of G bar, which definitely will belong to H bar, which implies that K will belong to H. Hence, the kernel is contained in H. So we have shown that the H we defined is actually a subgroup of G that contains the kernel K. Next, let H bar be normal in G bar. We have to prove that H is normal in G. For that, we are going to choose an element in H and an element anywhere in G. So let G belong to G and H belong to H. Okay. Normality of H bar in G bar implies what happens when we calculate the phi image of GH G inverse. Since phi is a homomorphism, it will become phi G, phi H, phi G inverse. Now phi H, due to the fact that H belongs to H, phi H must be in H bar, and phi of G and its inverse are both in G bar. So normality of H bar in G bar would imply that this belongs to H bar. Hence, by the definition of H, capital H, GH G inverse belongs to H. This implies H is normal in G. Okay, now we will prove the correspondence. Let S be the set of all subgroups of G bar and T be the set of leading and let T be the set of all subgroups of G which contain K. We are going to define a mapping style, say from S to T by this formula. If we take any element from S, then that is a subgroup of G bar, say H bar. By definition, this is nothing but the inverse image of H bar under phi. In the previous paragraph, we have proved that psi is well defined. See, there are two things. The first is that when we choose H bar from S, that means we are choosing a subgroup of G bar. For that, we have already shown that the inverse image of H bar under phi, which is nothing but H, is a subgroup of G. That means it's in T, provided it also contains K. But that is the case. We have shown that that is also true. Moreover, for a given subgroup H bar of G, its inverse image under phi is unique. There are nothing like two inverse images or three inverse images under the same function. It's unique. So that's why psi is a well-defined function. Now we will show that psi is both one-to-one and onto. Let H1 bar and H2 bar belong to S such that phi inverse H1 bar, which is psi of H1 bar, is equal to psi of H2 bar. So that means here we are assuming that the images of H1 bar and H2 bar under psi are the same. We have to prove that the inputs are also same. That will show that the function is one-to-one or injective. So this is equal to phi inverse of H2 bar. Okay. Now our aim is to show that this is contained in this. That means this is contained in this and also this is contained in this. So let H1 belong to H1 bar. Okay. Then if H1 belongs to H1 bar, then okay, ontoness, yes, then ontoness of phi, it's given that the original homomorphism is an onto mapping from G to G bar, and since H bar is an element of, H1 is an element of H1 bar, and this H1 bar is contained in G bar, so H1 is also in G bar, and that's why it will be the phi image of some element in G due to that ontoness. The ontoness of phi then implies that H1 is equal to phi of, say, H3 for some H3 belonging to G. Okay. Now phi of H3 equal to H1, it belongs to H1 bar, implies H3 belongs to phi inverse of H1 bar, because that's just the definition of the inverse image of a subset, that any element in it is such that its phi image is in the given subset. But then H3 also belongs to phi inverse of H2 bar. Now we can use this equality, and hence H1 equal to phi of H3 must belong to H2 bar. We have thus shown that any element H1 in H1 bar is again in H2 bar. Thus H1 bar is a subset of H2 bar. From symmetry, since there is nothing special about H1 bar or nothing special about H2 bar, so whatever we did with H1 bar is an exact similar thing also can be done with H2 bar, giving us the ultimate conclusion that H2 bar is also contained in H1 bar. So instead of writing those things, we just simply write from symmetry we have H1 bar equal to H2 bar. So our function psi is 1 to 1. Okay, now next we want to prove that psi is onto. For that we have to choose any element of T and show that it's the psi image of some element in S. So let H be any element in T. Then what does that mean? It means that capital H is a subgroup of G that contains the kernel K. Then H is a containing K. Okay. Now we have to somehow find an inverse image of this H. Consider the subset phi of H Okay, so it's the image of the subset H under phi, ordinary image, not inverse image. Note that E bar equal to phi of E belongs to phi of H. Because H originally is a subgroup of G containing K, nevertheless it's a subgroup, so H will contain the identity element. So that's why its phi image will by definition belong to phi of H. So phi of H is a non-empty subset of the domain group G. Our aim now is to show that this phi of H is actually a subgroup of G. Let G and H belong to H. Then GH will also belong to H because H is after all a subgroup of G, and phi of G, phi of H, which due to the fact that phi is a homomorphism becomes equal to phi of GH. Now because GH is in H, so phi of GH will belong to phi of H. So any two elements of phi of H which will look like this, phi of G and phi of H, for some G and H belonging to H can be combined, and the product is again an element in phi of H. Also, since G inverse belongs to H, we have phi of H is a subgroup of G bar. Now we aim to show that the inverse image of this phi of H is actually equal to H. Thereby we will show that the psi image of phi of H is actually equal to H, and hence psi will be proved to be onto. Okay. Now we claim that phi, okay, we can write like this also, it will become more clear. Phi of h, which is phi inverse phi of h, is equal to h. Note that from this containment, we immediately have h a subset of phi inverse of phi of h. Okay, because if you take any element here, that element will look like this, and this definitely belongs to phi of h, because h belongs to h, and this just simply says by the definition of this set that h must belong to this set. So any element of h is in this set, so h is a subset of this set. Next, let y belong to phi inverse of phi of h. Then phi of y is in phi of h, and so phi of y will be equal to phi of h for some h belonging to h. Note one thing, that from here we cannot immediately conclude that y belongs to h. All this relation says is that phi of y is an element of phi of h, so it will be equal to phi of something from h. We still don't know about y. Now what happens to phi of yh inverse, say? Since phi is a homomorphism, we can write phi of y, phi of h inverse. But now we use the fact that phi of y is nothing but phi of h. So this is equal to the identity element in G bar. But what does this imply? The phi image of yh inverse being the identity, it just says that yh inverse belongs to the kernel of phi, which implies that this belongs to the kernel of phi. Now note that since h is a subgroup of G containing k, so this element in k will also be in h. Since k is contained in h, we have yh inverse belonging to h, and this finally implies that y belongs to h. It's because you see YH inverse will be an element of H. Say YH inverse is equal to H prime. You then post multiply both sides by H. That will give you Y equal to H prime H. H prime and H are both elements of H, so their product is again an element of H. So that's how you get Y belonging to H. So you see that not only do we have this relation, but the other inclusion is also true. Hence, phi inverse of phi of H is also contained in H. We have thus proved that H is equal to phi inverse of phi of H, which is nothing but psi of phi of H. Since we proved that phi of H is a subgroup of G bar, so phi of H actually belongs to S. Here, so that just shows that any element of T has an inverse image in S under psi. Hence, psi is onto, and this completes the proof. There is one more similar result, but it's written as theorem. This is theorem 272. Let phi be a homomorphism. Okay, so the beginning is the same. Homomorphism of a group G onto a group G bar with kernel K, and let n bar be a normal subgroup of G bar, sorry. Let n be defined like that, that is the inverse image of n bar under phi, x belonging to G such that phi of x belongs to n. Then by the previous lemma, we know that n will also be a normal subgroup of G, and in fact it will contain the kernel K. Then the quotient group G by n is isomorphic to the quotient group G bar by n bar. Equivalently, the quotient group G by N is isomorphic to the quotient group G bar divided by K. Oh, instead of G bar we will take G by K. Okay. By N by K. Okay. So here we are given a normal subgroup N bar of G bar, and N is the inverse image of N bar. This is going to be N bar, no? Yes. Inverse image of N bar under phi. We already know that N is normal in G. So both these quotients G by N and G bar by N bar can be formed. Now this theorem says that they are actually isomorphic, and this same statement can be equivalently written like this. So let's see the proof. So we will have to define a function from G to G bar by N bar that is a surjective homomorphism, that is an onto homomorphism whose kernel turns out to be N. Okay, so let's just start by defining such a thing. Defines again we can call it psi, because this is a new proof. Psi from G to G bar by N bar by this rule. Psi of G is defined to be equal to N bar phi of G. The question is, does it make sense? First of all, you see, G is an element of G, and we already have a mapping phi from G to G bar. So phi of G will be an element of G bar. So we can in fact form the coset N bar phi of G of the normal subgroup N bar of G bar. And that coset is naturally, it is going to be an element here in this second codomain. Now comes the question of having unique images for a given element. Oh, but that is clearly, that is clear. You have G here, for that you get a unique inverse image. You don't get two such things. Since phi of G is in G bar, this is in, and so the map psi is well defined. Okay. Is it a homomorphism? Let's verify that. Let N1 G1, oh sorry, this is not N1, this is NG1, or rather we are trying to show that the map is a homomorph. Okay, let G1 and G2 be two elements in G, because the domain is just simply G. Then phi of G1 G2 by definition is this, sorry, psi of G1 G2 by definition is this. which becomes equal to, since phi itself is a homomorphism, phi of g1 times phi of g2, and since n bar is normal in g bar, of which phi of g1 and phi of g2 are two elements, so it will be the product of these two cosets. Which is psi of g1, psi of g2. So psi is a homomorphism. Now next we want to show that psi is onto. For that, let A belonging to, this time we have to take in fact a coset n bar, say z, belonging to g bar by n bar, a coset of n bar in g bar. That means this z is coming from g bar. Since phi from g to g bar is onto, there exists an element u belonging to g such that z is equal to phi of u. Then n prime z is equal to n prime phi of u, which becomes psi of u, because that's the definition of psi. Thus psi is onto. So psi is a well-defined onto homomorphism of G onto G bar by n bar. Now comes the question of the kernel of psi. Since it's a homomorphism, it will have a kernel. For any n belonging to n, we have how has n been defined? N has been defined to be the set of those elements in G which are mapped by phi onto elements in n bar. So since this is an element of n, so phi of n will belong to n bar. Thus psi of n, which is n bar phi of n, since phi of n belongs to n bar, so this coset will be equal to n bar itself. Which implies that n is contained in the kernel of psi. Now we will show that the kernel of psi is also contained in n. Next, let nu belong to nu b any element in the kernel of psi, then n bar is equal to psi of nu because it belongs to the kernel, but by definition this is equal to n bar phi of nu. Hence, since n bar is it's a normal subgroup of G bar but nonetheless a subgroup, so we have the fact that phi of nu belongs to n bar. Now if phi of nu belongs to n bar, that means what? Nu will belong to n, which implies, by the definition of n, nu belongs to n. So any element in the kernel of psi is in n. Nu was chosen to be any element in the kernel of psi. We have found that it must be in n. Thus, n itself is the kernel of psi. So we now have all the pieces. This is a homomorphism of G onto G bar by n bar, whose kernel is n. So by what was that? Lemma 271 or Theorem 271. I don't have the reference number here. Anyway, you are going to understand what we are going to write here. So G by n is isomorphic to G bar by n bar. Also, or rather, let's just write like this. Equivalently, we have to show that G by n is isomorphic to G by k by n by k. Now, G by k of course is isomorphic to G bar because originally we have our homomorphism phi from G onto G bar with kernel k. So G by k must be isomorphic to G bar. Also, the restriction phi from n to G of phi to n, instead of considering the phi on the entire group G, we can also make its domain smaller. We restrict the function to the subgroup n. If we do that, is actually a homomorphism of n onto means originally the function was onto n bar with kernel k. Why? You see, the situation is like this. This is our G, this is our G bar, and this is suppose N, and we already know that N contains the kernel K. So the kernel K is here. Now we are restricting the total function phi onto N, and we are claiming that it actually is a function from N into N bar. Is that true? You see, if you take any element in N, then by the very definition of N, the way we have defined N in the statement itself, its phi image must belong to N bar. So that's why the restriction of phi from G to N actually is a function from N to N bar, and since it's a restriction of a homomorphism, this restriction itself is a homomorphism. So this is a homomorphism from N to N bar, and the kernel is K. Why? Because the entire kernel of the original bigger homomorphism is contained in G. So these are the only possible elements which are mapped by phi onto the identity element of G bar. So since all of them have in fact come inside N, so the kernel will be the same. Now the only thing left for us to understand is why is phi onto N bar. You choose an element of N bar, say anything, say B. Since the original function phi is onto, so we know, so B is here somewhere. Since we know the original function phi is onto, so there is an element A belonging to G such that phi of A is equal to B. Note that this immediately does not tell us that A has to be in N. Okay, we just from using the fact that phi is onto, we get this. But now you combine these two pieces of information, you then have phi of A, an element in N bar. And so by the definition of N again, A then must be an element in N. So that's why every element in N bar has an inverse image, not just in G but actually inside N. So this restriction as a function is onto. That's why we are saying that the restriction is actually a homomorphism of N onto N bar with kernel K. So because of that, what can we write? N by K is isomorphic to N bar. Now what you do, you just replace this G bar here by G by K and N bar here by N by K because they are isomorphic. So hence G by N is actually isomorphic to G by K by N by K. Okay, so this completes the proof of the theorem. These theorems will be useful. Particularly the correspondence theorem is going to be very useful. I mean the previous lemma. After this we have the exercise set, which we will do in another video. If you encounter any doubt, or if you want to ask something about these things, you are encouraged to write in the comment section below. So that will be all for group theory tonight. So see you in the next video. In the next video we will discuss the exercise problems, and one of you actually has requested for fields. We will start fields along with vector spaces. Just let us first finish the ring theory problems. There are a few left in the last section, so we will finish that as quickly as possible, and then we will jump into vector spaces and fields. So see you in the next video. Until then, it's me, Lucifer, from a mathematical room. Have a nice night.